Okay, let's dive right into this explainer. Today, we're unraveling how a simple, quiet walk in the snow led to literally one of the most explosive discoveries in human history. We are talking about the exact moment humanity realized we could split the atom. It's this wild story of incredible minds, historical accidents, and the beautiful way that two totally different ways of thinking can suddenly just click together to reveal a hidden truth of the universe.
So, picture this. It's December 1938 in Kungälv, a tiny town in Sweden. We've got two exiled physicists, Lise Meitner and her nephew Otto Robert Frisch, meeting up for the Christmas holidays. Both of them were victims of persecution in Nazi Germany. Frisch had lost his position in Hamburg and found a haven in Copenhagen, while Meitner had recently been spirited out of Berlin to Stockholm. They sit down at breakfast, completely unaware that they're about to crack a downright impossible scientific mystery. And you really have to imagine the headspace they were in here. They had these incredibly heavy personal worries on their minds. I mean, Frisch's father was actually incarcerated in Dachau at the time, but suddenly their attention gets entirely hijacked by a single piece of mail. Meitner had just received a totally baffling letter from her longtime colleague back in Berlin, the brilliant chemist Otto Hahn. Hahn, along with his colleague Fritz Strassmann, had been continuing these experiments they'd all started together, but Hahn's letter detailed an experimental result that completely defied the laws of physics as they knew them. When they bombarded uranium with neutrons, the resulting material contained barium. Now, Meitner instantly rejected the idea that Hahn had just made a mistake. He was simply way too good of a chemist for that. If he said he found barium, well, he found barium. But to any physicist at the time, this was pure madness. It broke every fundamental rule of how atoms were supposed to behave. How in the world was that physically possible?
To really grasp why Hahn's letter was such a bombshell, we have to look at how insanely fast the study of radioactivity was moving back then. In just a handful of decades, we went from Henri Becquerel accidentally discovering uranium rays in a dark desk drawer in 1896 to the Curies isolating radium and polonium. Physics was sprinting forward at an absolute breakneck pace. By 1932, James Chadwick discovers the neutron, which basically handed scientists a brand new tool to trigger nuclear transmutations. And then in 1934, Enrico Fermi used those exact neutrons to bombard uranium, assuming he was creating entirely new, heavier elements that he called oscinium and hesperium. Fermi actually won a Nobel Prize for this.
But here is the crux of the mystery. Bombarding a heavy nucleus like uranium was really only supposed to chip off tiny little particles like alpha or beta particles, or maybe build it up into a slightly heavier element. The golden rule was simple. You chip the rock, you don't crack it in half. Yet Hahn's chemical analysis proved he had somehow produced barium. And barium is an element sitting right in the middle of the periodic table, weighing roughly half as much as uranium. To put that into perspective, getting barium out of uranium was literally like throwing a marble at a bowling ball and watching the bowling balls split perfectly into two smaller bowling balls. It was utterly absurd. Under the current laws of nature, it made absolutely no sense.
So, Meitner and Frisch are out walking in the snow, trying to make sense of this sheer impossibility, and they start talking about a concept from 1928, invented by George Gamow, known as the liquid drop model. Gamow had proposed that a nucleus behaves remarkably like a tiny droplet of fluid. The collection of particles inside that nucleus exert this massive outward pressure, but they're held tightly together by an inward surface tension. This specific moment out in the snow brilliantly illustrates why the author Arthur Koestler called creation the synthesis of two matrices of thought. Because, if you think about it, these two minds were the absolute perfect puzzle pieces for this exact problem. Meitner brought her deep knowledge of the Berlin tradition, specifically the static mass defect calculations, focusing on how surface tension balanced out the repulsive charge of the protons. Meanwhile, her nephew Frisch brought his deep understanding of the Copenhagen tradition from working directly with Niels Bohr, which focused heavily on the dynamic, vibrating excitations of the nucleus.
Now, you might be wondering, why didn't the great Niels Bohr figure this out first? Bohr was easily one of the greatest scientific minds of the era, but he completely missed this, basically because he was blinded by his own assumptions. His own work from 1936 assumed that if an excited nucleus was hit hard enough by a neutron, it would behave like an elastic solid. It would just boil off tiny particles one by one, or if you hit it with a massive amount of energy, it would just explode entirely into a shower of random shrapnel. A neat, clean split into two relatively equal halves, that literally wasn't even a possibility in his mind. So let's break down the exact physical steps of their realization during that snowy hike. Trying to visualize Hahn's bizarre barium finding, Meitner sketched a circle in the snow. Frisch takes one look at it and visualizes an end-on view of a dumbbell.
basically an elongated liquid drop with a pinched constriction right in the middle. And suddenly, it clicked. They realized that the immense electrical charge of the countless protons inside a heavy uranium nucleus would push against each other so intensely that it would diminish the surface tension to almost zero. That drop was wildly unstable. Just a tiny, tiny nudge from a neutron would cause that dumbbell to pinch off and fly apart.
And think about the sheer scale of what they had just uncovered. Standing right there in the winter cold, Meitner basically had the entire mass defect curve memorized in her head. She rapidly calculates that the two resulting halves, like barium and krypton, would be slightly lighter than the original uranium atom. By applying Albert Einstein's famous mass-energy equivalence formula, EMC², she realized that this missing mass was converted entirely into energy. And we're not just talking about a little spark. A single split uranium nucleus would release an astronomical 200 million electron volts. The two halves wouldn't just gently separate. They would violently fly apart with an unprecedented, terrifying force. Having cracked the mystery, they rushed right back to their respective labs to document what they'd found. And interestingly enough, Frisch actually asked a biologist friend what the term was for when a single biological cell divides in two. The answer, of course, was fission. So, borrowing a term from biology for physics, they named this terrifying and magnificent new nuclear process fission. They quickly composed this short, elegant 3-page note over the telephone and submitted it to the scientific journal Nature in January 1939. Now, before the paper was even officially published, Frisch caught up with Niels Bohr in Copenhagen on January 3rd to tell him what they had deduced in the snow. When Bohr heard their elegantly simple solution utilizing the liquid drop model, he literally slapped his own forehead. I just love this visual, because you can imagine the sheer astonishment. He was deeply shocked that the entire physics community had been totally blind to what was sitting right in front of them all along. The pieces of the puzzle had been on the table since 1928, but it took Meitner and Frisch to finally put them together. The legacy of their incredible synthesis lives on today, heavily bridging the gap between historical physics and modern tangible history. Just to give you an idea of how foundational this exact moment was to human civilization, a rare off-print of their original 1939 paper recently sold at a Christie's auction for $12,600. It is a monetary testament to the heavy historical weight of that specific document. That single conversation in the snow fundamentally shifted the trajectory of energy, warfare, and global geopolitics for the rest of time. As we wrap up this explainer, I really want to leave you with a thought about the profound nature of discovery. Meitner and Frisch didn't invent some new math or find a brand new particle hiding in the snow. They simply brought two completely different traditions of thought together to interpret data that already existed. It really makes you wonder, what impossible mysteries could we solve tomorrow if we just combined the right perspectives today? Look at your own impossible problems through a completely new lens. You might just split the atom.